Welcome to week 4 of our course, Boltzmann Law, Physics to Computing. This is the first lecture of week 4. Now, this weeks 4 and 5, that's the quantum part of this course, loosely speaking, they correspond to weeks 2 and 3. Mathematically, as you'll see in this week 4, we'll introduce this equation, which is looks like a lot like the classical Boltzmann law. It's just that instead of a probability distribution function, we have this density matrix. And instead of energy, you have the energy matrix or the Hamiltonian. Whereas in week 5, we'll introduce this quantum transformation law, which loosely again corresponds to the classical transition matrix, where you had a probability distribution function that evolved with time. Here you have a wave function that evolves with time. Anyway, so let's get started with week 4. So how do you go from this classical Boltzmann law to what I call this quantum Boltzmann law? Now, in order to make this transition, it is convenient to start from the bipolar representation. If you remember in lecture 2.4, we introduced this bipolar representation, which is equivalent to the binary representation which we commonly used in weeks 2 and 3. And the idea is here the spin has these two values 1 and 0, whereas here it has the values +1 and -1. Now for the purposes of making this transformation to the quantum Boltzmann law, the bipolar one is more convenient. It corresponds more directly. Okay, so this is where we'll start. Now, for starters, let's ignore this interaction term and just think of one spin, right? And for the one spin then, we don't need the second term, and m times h is basically just, these are both scalar quantities. So you have this energy has these two values corresponding to m equals +1 and m equals -1. Now, in lectures 3 and 4 of this week, we'll pick up interactions between spins. For the moment, let's just focus on one spin. Now, this description applies to, again, this classical spin. So it's like a classical magnet. But what we want to describe now is quantum spins, and the best example of that is a single electron, because every electron is actually like a magnet, but it's a quantum magnet. And what I'll try to describe in this lecture is what that means and how you describe it. So this elementary magnet, you might think, okay, I've got this electron, it has no particular preferred direction, unlike a magnet where you could say, okay, this is the long axis. Well, the electron has no particular axis. It could point in any direction. And so you might say, well, what I really need to do is take my basic description that I had before and turn it into a 3D spin, something where the magnetization or the magnetic moment can have three components, mx, my, and mz. And instead of this one parameter h, I'll now have a hx and a hy and a hc. And I could write the energy as, say, h dot m. Now, if we did that, then I guess what I'd like to point out is that that doesn't quite correspond to what people see experimentally. And that is why you need this quantum description. So suppose we put all h is equal to 0. Then the energy is equal to 0, which means regardless of which direction the magnet points, this elementary magnet, the energy is the same. And so when you apply Boltzmann law, you'd say all directions have equal energy and hence equal probability. Well, so if I went in and measured a particular component of this magnetic moment, say the z component or the x component or the y component, you'd think that you'd get all values between -1 and +1, because after all the magnet could be pointing in any direction, and so its z component could have any value between the extremes. Well, About 100 years ago, the Stern and Gerlach reported this experiment, which essentially revolutionized our conception of this electron. And what they showed was that when they measured mx or mz or my, they saw only two values, -1 and +1, not this continuous spectrum of values. And of course, in science, facts come first. And so if the facts don't fit the math, then you have to change the math. So question is, how do we change our mathematical description to fit this new facts? Now, so the quantum, and that's how the quantum theory evolved. And in the quantum theory then, the m, this magnetic moment, gets replaced by a operator sigma, which as you'll see is a 2 by 2 matrix. So instead of h dot m, you write this energy matrix, or what's called the Hamiltonian matrix H, which is h dot sigma. Now, what is this sigma? Well, we have these three polyspin matrices, one corresponding to each direction, sigma z, sigma x, and sigma y. And these are the three matrices. And so h dot sigma means hx times this matrix plus hy times that matrix plus hz times the sigma z matrix. And when you measure any quantity, let's say you want to know, I measure mz, what values will I get? And the answer is, the measurement will only yield eigenvalues of the corresponding operator. So what are the eigenvalues? Well, for sigma z, since it's diagonal, it's easy to see the eigenvalues. It's +1 and -1, whatever's on the diagonal. But what about sigma x? Well, it's not as easy to see, but you can easily check what the eigenvalues are. The answer is it's still +1 and -1. And if you look at sigma y, it looks different, but here too, the eigenvalues are +1 and -1. So whether you measure mz or mx or my, what you'll measure will be the eigenvalues of the corresponding operator, and those are -1 and +1. And that obviously fits the facts here. Now, quantitatively, how do we predict probabilities of measuring -1 and +1? So that is where this density matrix comes in. So classically, the probability was, as you know, related to the energy. Now we have a density matrix, which is exponential of -h, h being this energy matrix or Hamiltonian matrix. Now, one side note, that this H matrix is Hermitian. And Hermitian means that it is equal to its conjugate transpose. So if you look at the ij component, it's equal to the ji component complex conjugate. So all these three spin matrices, you'll notice, are Hermitian. Sigma z is Hermitian because there isn't any off-diagonal element, and hii and the diagonal elements, h11 or h22, those are all real. So they are, of course, equal to their complex conjugate. In sigma x, again you'll notice 1 is equal to its complex conjugate. And here also, here minus I is equal, and this is the complex conjugate is plus I. So H is Hermitian, and so is rho, which is obtained by exponentiating this H. And I should note that this exponentiation is in a matrix sense, not in an element by element sense. And these will become clear when we look at the actual examples. Now, if you write out this matrix then, this Hermitian matrix, it will always have this form. There will be real quantities on the diagonal. The off-diagonal elements can be complex, but then there will be equal. If this is C, this will be C star, complex conjugate. Now, these diagonal elements basically give you the probability of measuring mz equals +1 or -1. Now, what about mx and my? Well, you might be tempted to say, oh, the probabilities of mx, I should look at the off-diagonal terms. Well, no, that won't quite work, because after all, these off-diagonal elements are complex and they cannot be interpreted as probability. But the general rule for finding the, for predicting measured values is the following, that given any quantity S, there is a corresponding operator. And the way you find the average expected value of that quantity is by taking the trace of this operator times the density matrix. And when you take trace, it doesn't matter in what order you multiply the matrices, so you could multiply the density matrix times the operator. Answer would be the same. So if you wanted mx, well, you take whatever density matrix you have, multiply it by the operator representing mx. If you want my, take the density matrix, multiply it by the operator representing my. And then take the trace and you'd have the average value. Now, what if I wanted to predict the value of the correlation between mx and my? So I go and measure both mx and my. And I want to know the average value. And you might say, well, that's simple from your law, because I could define the operator for mx, my as sigma x, sigma y. Well, not quite, because what's not clear is, should I use sigma x, sigma y, or sigma y, sigma x? And now when you are talking of numbers like mx and my, of course, the order doesn't matter. But here we have matrices. So matrices, A times B is not necessarily equal to B times A. And in this case, actually it isn't. You can check it out. If you multiply sigma x times sigma y, you'll get plus I times sigma z. And if you take sigma y times sigma x, you'll get minus I times sigma z. And neither of these are actually Hermitian anyway. So the bottom line is, if you really wanted to know what's this expectation value of this quantity, the quantum theory I just described to you wouldn't give you an answer really. Well, then how do we use quantum theory? And the answer is that, well, experimentally there is no way to measure mx and my simultaneously. If you could, then you see quantum theory would be, it would essentially fall. But it stands on the general experimental fact also that for these elementary spins, there is no way to measure two components simultaneously. You can either measure x or y or z, but not any two of them. And in general, whenever you have two operators, if they do not commute, meaning if AB is not equal to BA, then you cannot measure them simultaneously. And this applies to the x and y component, and also to the y and z component, and also to the z and x component. They all have this cyclic property, and which is actually, when dealing with spin matrices, this is a very useful property to remember. This set of equations, x times y is plus I times z, y times z is plus I times x, zx plus I times y. Now one last thing, and that is to calculate the probability. As you know, you also need to figure out this constant in front. And in the classical case, the idea is that all probabilities must add up to 1. And so this constant, this denominator z, is actually the sum of all the exponentials. The corresponding thing from the quantum law is that you see that diagonal elements of the density matrix, they represent a probability and they must add up to 1, which means the trace of rho must be equal to 1. And that leads to the condition that this quantity in the denominator should be equal to the trace of e to the power minus h. Okay. And so to sum up then, what we did in this lecture was we introduced this quantum version of this energy, which is that gives us this energy matrix. And you can use this energy matrix to find the density matrix, which is like the quantum version of probability. And once you have the density matrix, you can calculate the expected value. You can predict the measured value of any quantity using this rule, that for whatever quantity you're interested in, you have to figure out the corresponding operator and then perform this operation. So in the next lecture then, what we'll do is look at an example of a 1-qubit system and how you apply the rules we just laid down. Thank you.